Before coming directly to the subject, I will be keen to explain some terms that will help you to understand the subject. Number 1. Electromagnetic waves. Electromagnetic waves are transverse waves, just like the waves you watch in the sea, or when you give a tweak at one end of a rope kept on a table. The waves are characterized by crests and troughs. The distance between two consecutive crests or troughs is called the wavelength. The number of crests or troughs encountered by a particular obstacle line in the way of the wave in 1 second is called the frequency of the wave and is measured in hertz. It is actually the number of cycles completed by the wave particle in 1 second. It is obvious that longer wavelengths will have less frequency, hence less energy, and short wavelengths will have high frequency, hence more energy. The electromagnetic waves are a part of our daily life. The radio, the television, the X-rays, the microwave oven, the mobile phones, the GPS tracker, all are dealing with waves from a wide range of electromagnetic waves called the electromagnetic spectrum. It ranges from gamma rays, which have the lowest wavelength, to radio waves having the maximum wavelength. At one instant, there are so many waves passing through your living room that you cannot even imagine. But how do you manage this? You can manage this because among all the waves, only those waves which have wavelengths starting from 380 nanometers to 740 nanometers can be seen by us, and all other waves which are outside this range are invisible. Now, where do these waves come from? These waves come from the sun. Only the visible waves and some infrared and radio waves reach the Earth's surface, and the rest of the electromagnetic waves generated by the sun are mostly blocked by the atmosphere. This being the wavelength distribution of colors of the visible range, violet having the shortest wavelength and red has the longest wavelength. In fact, we can watch everything on this earth, like suppose we can watch an apple, because the apple molecules absorb all the visible waves except that with the frequency of the red light. Number 2, scattering. Now we will be concerned about the electromagnetic waves in the visible range only. That is from wavelength 380 nanometers to 740 nanometers. We may well assume that the average to be around 500 nanometers. Now the electromagnetic waves that are emitted from the sun travel all the way to the earth in 8 minutes at the speed of light. On its way, it has to face the Earth's atmosphere. But what is there in the Earth's atmosphere? Earth's atmosphere contains gas particles, mainly nitrogen and oxygen, whose particle size is below 1 nanometers. In addition to gas particles, there are also aerosol, dust, smoke, moisture particles, whose size varies from 100 nanometers to more than 1000 nanometers. Now, light waves strike the particles of the atmosphere and get scattered. Scattering means that the light waves get reflected after striking the atmospheric particles in all possible directions. The scattered light is visible to us as the color of the sky from the earth. In this animation, red, green and blue waves are shown scattering in the atmosphere. Whichever light scatters most will be the color of the sky. Now the question is why the color of the sky appears blue. To understand this, we have to understand scattering a bit more. The nature of scattering depends on the particle size. The average wavelength of visible light is 500 nanometers as already said. Now if the particle size is much less than 500 nanometers, which is the gaseous particles of the atmosphere, the scattering that happens is called Rayleigh scattering. Now watch this Rayleigh scattering animation. See the particle size which is much less than the wavelength of the blue and red light waves. Now let us animate the waves. What do you see? You see that the crest of the blue wave is touching the gas particle more often than the crest of the red light wave. So it can be said that blue light is more scattered than red light in Rayleigh scattering. Mathematically, we may say that in Rayleigh scattering, the intensity of scattered light is inversely proportional to the fourth power of the wavelength of incident light. That is, blue light is scattered at least 12 times more than red light. Now, if the particle size is equal or more than the wavelength of light, then the scattering that takes place is called Mie scattering. Now watch the Mie scattering animation. Here the particle size is greater than the wavelength of blue as well as the red light. Now let us animate the waves, and you can see that the crests of both the blue and red waves are always in touch with the particle. This means that all visible light waves of every wavelength are scattered the same amount in Mie scattering. The scattered ray is a mixture of all colors, or in other words, in Mie scattering, always the scattered light is white. When compared to Rayleigh scattering, Mie scattering scatters more in the forward direction, whereas Rayleigh scattering is scattered equally in both forward and backward direction. The ray that is scattered backwards is lost, and the intensity of that color reduces drastically after successive scattering. Now, in the daytime, the sun ray has to travel this much length of the atmosphere. Here, Rayleigh scattering takes place. At the starting, violet, having the lowest wavelength, scatters most. So the color of the sky should have been violet and not blue. But the sky is never violet, because mainly of two reasons. Number one, the visible spectrum from sun does not have all the colors in equal amount. This is because sun's radiation has more of red and orange and very less violet than blue. So violet color scatters away faster before reaching the Earth's surface. Number two, when visible light waves of different wavelengths come to the Earth, there is mixing of light waves. In this type of mixing, red, green and blue waves are waves of the primary colors, which are pure in the sense that the primary colors are original and are not the outcome of mixing of two different waves. All the other colors, however, are the result of mixing of the three primary color waves in different proportions. For example, when green and red color waves are mixed in equal proportions, we get a yellow color wave whose wavelength is intermediate between red wave and green wave. Violet, being the wave of the lowest wavelength, however, cannot be the result of wave mixing. After violet, the next shortest wavelength is the blue light, which is scattered most and the sky seems blue. During sunset and sunrise, the sky appears reddish-orange rather than blue. This is because during sunset and sunrise, light has to travel more length of the atmosphere than daytime. Due to this reason, the light waves having wavelengths shorter than orange light are scattered away before reaching the Earth's surface. Only red and orange light gets scattered and the sky becomes reddish at the horizon, from where the sun's ray is coming. The cloud appears white because the cloud particles are large moisture particles and Mie scattering takes place.